Jiva Krishnamurti.
Yes.
Transient behavior of the concentration is one. This is the talk after Andrei Zalizomsky. You see in your list. However, I will start.
Okay, so please go ahead.
Jeva Krishnamurthy, are you here to give your presentation? I will look in the attendees. Okay, Jiva. Okay, please. We see your presentation, but we cannot listen you.
Okay. Do you hear me?
Yes,
Yes.
Now we can hear you.
Yes.
To you all.
Please go ahead.
Yeah.
Now you have 10 minutes.
Okay.
Plus a couple of minutes for question or comments, please.
Okay. I am presenting the paper on behavior of the concentration of bipolar small ions monitored at Maitri, Antarctica, and its relevant and its correlation to radon and meteorological parameters. Just not able to.
Jeva, you are not in the presentation mode. We see your presentation, but not in the presentation mode. However, you can go ahead with your slide.
Okay. Is this okay now?
We see the starting slide, so you can go on.
Okay, thank you. The motivation of the study is the general fair weather DC electrical environment observed by Jiva et al. Showed the presence of an anomalous characteristics in the atmospheric electric potential gradient and area of current density. The background of atmospheric electrical environment is determined by the net concentration of bipolar small ions in the atmosphere. So, places like Greenland and Antarctica, where the Earth is covered by thick ice sheet and free from anthropogenic activity, provides a unique opportunity to investigate the role of ionization near Earth environment by secondary cosmic rays. Therefore, investigation of the characteristics of small ions, also called as air ions, is an important study. Some of the salient features are provided here. So the instrument used to study the small ions or air ions is the bipolar ion counter, and it functions based on Gaudian principle. It captures, it measures the ions in the size of 1.4, less than 1.4 nanometer, with electrical mobility 0.7 into 10 to the power of -4 meters square per volt per second. And the detection ranges are 0 to 10 power 6 ions per centimeter cube. The data selection is done based on that there usually the disturbed weather used to provide a very distorted data set.
Sorry, Jiva, we see only your first slide. Huh?
Pardon?
We see
It seems
your first slide.
yeah. It seems freezed on the first slide.
This is first slide. This second.
And we cannot see the second slide. You have to choose the presentation mode. Maybe it works.
Do you see change in the slides?
No.
No, we cannot. Turn off the share screen and turn on again the screen.
Do you see it now?
We see only the first slide.
Okay.
Okay, now it works. Now it's okay.
Okay, now I am showing in the presentation mode. Just you see. Do you see now?
We see the second slide, but we are not in the presentation mode. So please click on your slide by slide, and we will see. So now this is the second motivation, titled the motivation.
Is this
Then
okay?
click. Okay.
Do you see the change?
No, sir. I think you should make it into presentation mode and then share the screen. Yeah, now it is moving.
It's the fourth
But I want
slide.
What about now?
No,
Jeva,
it is not moving.
Jeva, try to do that. Close your presentation and your sharing screen.
Is this okay now?
Try to do that. Close your sharing and open your presentation in a presentation mode and then share again.
Okay, okay.
Okay, thank you. Sorry, but
Is it okay now?
yes, now it is okay.
Okay. Do you see change in the slides?
Yes, yes, now it works.
Okay, okay, okay. Sorry for the delay. Okay, the data selection is done. Let me put on my mic. The data selection is done based on the fair weather day condition. The fair weather day condition is a day free from snowfall, drifting snow, or blowing snow, etc. Because on this day we find the concentration of the ions used to fluctuate a lot, so those days were discarded. For the study of diurnal and seasonal variation, the hourly mean data is considered. For some case studies, we considered 1 second data and 1 minute average data. The study period is 2019 to 2021. So this is the view of a location of Maitri station, and you can see this is the permanent station where we conduct the experiment around the year, and to operate this, we also conducted a campaign by measuring the concentration of ions simultaneously at 2 locations without changing the permanent location. One is at closer to the lake side, and another one is far away from the station over the polar ice sheet. And you can see the lake here is partly melted. During winter, it is totally frozen. So the melting and freezing cycle has a lot to do with the variation in the concentration of ions. So the first Fourier transformation analysis of 13 days data shows that there is a dominant periodicity of 196 hours, 24 hours, and 12 hours also. But we don't consider 196 hours data as the number of data points are too less. So we are considering only the diurnal cycle, that is 24 hours data. In this, you can see the negative ions show a prominent peak, which is showing a prominent diurnal variation rather than these positive ions. So this is one of the key observation and key point of the study that we will be discussing in the further. So these are all the 3 consecutive days data are plotted here. In the top row, we see the hourly mean diurnal variation of negative ions and the positive ions. Here you can see that there is a broad maximum center around 12 noon, that is a local noon for Maitri. And here on the second day also you are seeing the same thing. And on third day, the magnitude of the concentration is reduced enormously. And the difference is that one. On these 2 days, the wind speed was less than 8 meters per second. And at noon hours, there was a trough. That means the wind speed has become almost calm on both of these days. On the contrary, On this day, the wind speed remained more than 12 meters per second. That is one difference between these two. When you look into the temperature remained in positive, that is more than 0 degrees centigrade for on these 2 days. Whereas on the third day, the temperature was well below 0 degrees centigrade, and the correlation coefficient between the total ions and temperature shows always a positive, that is 0.6, 0.6, 0.7, and the wind speed, it's a negative correlation, that is 0.9 and 0.8. On 22nd, when the wind was strong, the correlation coefficient is just opposite to this one. This could probably due to the production of ions or more due to friction among the invisible or visible particles of the snow that can generate excess ions. Then we wanted to see the role of radon, the exhalation of radon and thoron on the net concentration of ions. The exhalation rate is observed to be between 18 and 20 becquerel per meter square per hour. And this is nearly just 1/3 of the global standard, that is 65 becquerel per meter square per hour. And there is no any significant diurnal variation in the exhalation rate of the radon and thoron. So it has no any significant contribution. At the same time, the principal component analysis also shows that radon and thoron does not play any significant role in this production of ions and diurnal variations also. So in this query, we are seeing the monthly mean curves for this negative ions and positive ions. You can see in the summer season, there is a prominent diurnal variation, and this gradually disappears as the month season goes towards the summer. And in winter, we see a flat response. And again, in summer, it starts occurring, the diurnal curve starts reappear. So it has clearly been seen that there is a broad maximum in negative ions in summer season, and the shape of the magnitude is the 29 positive ions are maximum during the winter season. And next slide. So it has clearly been demonstrated that temperature and wind speed play a significant role in determining the net concentration of ions. The wind can disperse and dilute the concentration. That's why it has a negative correlation with the concentration of ions. But how does the temperature alter the concentration of ion is a question. By such literature surveying, it is found that the Leonard effect and electrostatic interface effect, these are all the two phenomena which can contribute negative ions to the air due to splashing of water. They can generate negative ions, and this electrostatic interface effect, there can be the water can retain the positive ions and it can charge contribute negative ions to the air. We will discuss about these two phenomena in the later stage. But to understand this one, if the water body and splashing water or melting process give additional ions to the air, then we should observe more concentration of ions closer to the lake water body or over the ice sheet comparing to the permanent station where it is on the open landmass. For this purpose, we conducted a campaign without changing the measurement at the permanent station, that is under open landmass, and then we kept moving the other ion counter. So when we measured this is the permanent station, the concentration remained at around 400 per centimeter cube, whereas at the field location closer to the lake, there is double the amount quantity of the concentration of the ions were noticed. So this indicates that as we go closer to the lake, the melting process produce extra ions to contribute extra ions to the air. Now we shifted the one ion counter to the polar ice sheet. In the polar ice sheet, you can see the top one is the place, the permanent site. Over the exposed land mass, we measured the concentration, and this is the second bottom figure is measured over the polar ice sheet. We can see that at the local noon time, the maximum gone up to 200 pounds per centimeter cube, this concentration. Whereas this concentration, though there was a diurnal very peak in the permanent station, but it is not as significant as it is with the polar ice sheet. So it is clearly from this we understand that the melting process contributes more ions to the air. And another important feature we would like to mention is that when there is a signature at 0 to UT and 0 for UT, the simultaneously we observe a prominent, I mean, we cannot say something, a spike like signature. So this must be having, since we observed it at both the location, there must be a common source which can ionize the neutrals closer to the surface, and that could probably be the external sources like secondary cosmic rays and the cascade effects of the same. So the next thing we would like to say is that 3 consecutive season we have plotted. You can see this in the 2018-19, we see the negative ion concentration is more, and the diurnal pattern is also more. In the second year, we see the broad maximum, but the concentration is very low. In the next year, further it is deteriorated further. So in winter, there is no change at all. It is almost the pattern, whatever, everything. When we analyze the temperature variation, we saw that the temperature in the 2018, it was -2 degrees. That was the warmest month among all the 3 seasons. So this implies that when the summer season is warmer, the production of ions are more in that particular season. And if it is not enough warmer, the production rate remains low. At the same time, we would like to say that this provides the background value of concentration of small ions are about 250 per centimeter cube, and the positive ions are about 400. While we would like to say that the excess negative ions in summer is contributed by either Leonard effect or electrostatic interface effect, whereas the positive ions probably due to this electrode effect. So the Leonard effect basically is in the Leonard effect, ions are generated from the surrounding air molecules and contributed themselves negatively to the water droplets and collide with each other. With that, the air is acquiring negative charges. In electrostatic interface also, during the ice melting, there develops a charge separation. In that, the water body acquires either zero charges or negative charges. On the other hand, the air acquires either zero charges or negative charges. So the water body remains positive charges and the negative air becomes negative. So these processes contribute the negative air to the air. At the same time, the source of positive charge can be explained using the global electric circuit concept, through which the positive ions are deposited close to the surface. When they don't have opposite charge to neutralize it, there is a thin layer is formed close to the surface, and that contributes the excess positive charges, space charge we can call it. And that is why places like in Antarctica and Greenland, there will be a layer of electrode layer closer to the surface, and this is due to the space charge. The positive charges delivered to the earth through the global electric circuit concept. The simultaneous signatures recorded at 2 different locations is a unique result, as it might be due to the consequence of external ionic sources. So we are planning to explore the link of ionization through the external sources that would provide us ample knowledge towards understanding the solar terrestrial weather and climate issues. We are planning to intensify the campaign in the forthcoming season. And with this, I thank you all for watching this one, and thank you.
Okay. Okay, thank you, Jiva. Any question for Jiva? Short question, please. Then we can move to the next presentation.
Thank you.
And so according to the list, now we have Shipra Sina, I'm right? Hemispheric asymmetry in the cosmic noise absorption response during intense solar flare events. Are you there, Ship?
Yes, I'm here. Am I audible?
Yeah, we can see your screen now, yes.
Yeah, I have a pre-recorded video, if you may please play that.
Okay.
Yeah.
Please, Shivra, Shibra, go ahead. Thank you.
My voice is not audible in the video.
No.
No, no, no.
The video seems to be muted.
Hello and welcome to today's talk. My name is Shreedevi and I'm from Indian Institute of Geomagnetism. The topic of my today's presentation is hemispheric asymmetry in the cosmic noise absorption response during intense solar flare events. This is the outline of my presentation. I will start with an introduction of what solar flares and associated cosmic noise absorption are, the instrument that we use to measure this cosmic noise absorption. Followed with it, I will discuss two intense solar flare events that occurred on 6 September 2017 and 10 September 2017, and then will be the discussion part. So, what are solar flares? So, solar flares are sudden release of magnetic energy from the surface of the sun, causing sudden brightness of the photosphere that can last for a few minutes or 2 hours. Now, during these solar flare events, UV and soft X-ray emissions may increase by several orders of magnitude, thereby enhancing the ionization in the entire solar illuminated part of the ionosphere. Now, this will lead to a corresponding increase in the absorption of cosmic radio noise, and these absorptions are also called solar flare associated CNA or SCNA, and these will last for the duration of the entire solar flare event. Now, what actually cosmic noise absorption is? So, cosmic noise refers to the background radio frequencies of solar or galactic origin, and they have constant intensities during geomagnetically quiet periods. Now, when these waves travel through the ionosphere, they interact with the medium and can get attenuated in the ionosphere. Now, in the process of attenuation, a part of these radio waves gets absorbed in the ionized medium. And enhanced ionization will lead to more absorption of these waves, and hence a decreased intensity will be observed. So a difference between the intensities of radio waves during quiet period and disturbed time gives the absorption value, which we call cosmic noise absorption or CNA, and it is measured by using an instrument called rheometer. Now, rheometer is actually an array of dipole antennas which are tuned into a certain frequency, in this case 38.2 megahertz, and they observe a constant pattern during quiet time, which is called QDC or quiet day curve. During disturbed time, these intensities get absorbed and we get decreased signal. And the difference between the quiet day curve and the disturbed day curve gives the value of the CNA. So more higher the CNA means higher there was ionization in the ionosphere. So during solar flare events, if we compare locations with the help of CNA, we can get an idea of which location was ionized more as compared to the others. So for our study, we took high latitude stations, which are shown by blue star in this map. And for studying the hemispheric asymmetry, the two stations that we considered was Abisko in Finland and Metri station, which was at Indian Antarctic base. The other station data sets were used for additional information, which we will discuss later. So coming to the first solar flare event, which was on 6 September 2017. On this day, two X-class flare occurred, X2.2 and X9.3 class flares. So we have calculated the CNA by the process we just discussed before for Canadian station and for Huseful and for Metri, and these stations are arranged from lower to higher latitude. This plot has been taken from So the Nitya Geophysical Observatory website. The data sets were not available, but the plot was. So we have taken it for comparing. Now, for the X2.2 class flares, most of the stations in the left panel did not show absorption except for Husefeld and Metri. They did show some absorption. For X9.3 class flares, comparatively more absorption was seen in all the stations. And for the Finland stations, both the events observed absorption, but X9.3 class flare observed more absorption than X2.2 class. For the second event, which occurred on 10 September 2017, X8.2 class flare was observed for
The video was stopped. We cannot see the video anymore. We have lost the connection with the presenter.
Maybe she lost the connection. Shibra, Shina, if you have the last slide, the conclusion of your investigation, please share your screen and let us know about your conclusion.
Yeah, okay, I'll do that.
Yes, please.
Can you see the full screen?
Yes, yes, we can see.
Okay, so I think the video stopped here, right?
Right.
Yeah. So the second event was on 10 September 2017. And this day it had X8.2 class flare. So this red box actually indicates the time of the start and the end of solar flare. So during this day, most of the stations did show CNA observation, both Canadian, Husefeld and Finland station, except for Metri. We did not observe any CNA in Metri stations. And this table, I have summarized all the stations' CNA values to compare. So first we'll concentrate on the first two stations, which is Metri and Abisko, for looking into the hemispheric asymmetry. These are near conjugate stations, as I have shown in the map earlier. So for X 2.2 class flare, Metri had 0.3 dB. CNA value and Abisko had 1.5. For X9.3, Metri had 1 dB and Abisko had 2.5. For X8.2 class flare, Metri did not show any absorption value and Abisko had 0.8 dB. So comparatively, Abisko always had a higher CNA observation as compared to Metri. So this asymmetry can be because of two reasons. First is the background geomagnetic condition. Now, this whole month, September 2017, was very active in terms of solar flare. There was always a solar flare happening every other day. So the associated PCA events can be contributing to the additional CNA that is being observed in Abisko, as Abisko lies in the auroral region, so and Metri in the subauroral. So it's possible that these PCAs did reach Abisko and not Metri. So there was additional CNA observation in Abisko and not in Metri. And another could be solar zenith angle. Although we did consider September month because it is near equinox, so we expected similar illumination over the entire hemisphere, but still there was some difference in the zenith angle of Metri and Abisko. And for higher zenith angle, we expect less absorption because that area will be less illuminated. And that is what we see here also. Metri had always higher solar zenith angle as compared to Abisko. That's why it observed less absorption. But there were several other stations, Canadian stations, which had less solar zenith angle, but did not show any absorption. In fact, if we see this X9.3 and X8.2 class flares, then for these stations, X9.2, X8.2 class flare had more absorption as compared to X9.3 class flare, even though X9.3 had less solar zenith angle and higher class comparatively. Now, this can be because of the duration of the flare event. As we can see that X8.2 class flare lasted for almost an hour, and X9.3 was for hardly 15 minutes or so, and X8.2.2 was also for 20 minutes or something, and this was for comparatively a longer period. So maybe the time duration of the flare is also responsible for the absorption. So this is the conclusion of my high latitude CNA observation during these flare events. Thank you, and I'm open for questions.
Okay, thank you, Shipra, thank you. And Giorgiana, you raised your hand. Your hand, please.
Yes, just if just one short question or comments from the audience, or we go ahead and you can contact, of course, later Shipra Shina. Please, any
Yes.
question?
I have one question, me, or remark. Do you plan to have more rheometer in the south hemisphere?
Sorry,
Not maybe you, but in your community. Are there some group which plan to install more rheometer there in Antarctica?
Well, I'm not aware of that as of now, but I will look for that.
Okay, thank you. Because there is a lack here.
Yeah, yeah, you're right.
Thank you.
Thank you.
Thank
Okay.
you. So, Mimo, we can
move.
go to the next.
Yes. Nicolas Bergeot, overview of the
Yes.
SCAR expert group GRAPE, GNSS research and application to polar environment, activity 2012-2022. Please.
So, can you see my screen? Can you see me? Can you see my presentation?
Yeah.
Yes.
Okay. I don't ask if you can smell me because it's not it's a video conference. So let me present you the results from GRAPE. So GRAPE is an expert group from SCAR, which is a joint physical and geoscience group. It stands for GNSS Research and Applications for Polar Environment. It's managed by Giorgiana, and I am the Deputy Chief Officer. So the GRAPE main objectives is to, first, it's the 10 years of GRAPE. It has been launched in 2012, so 10 years ago in Portland. So happy birthday to GRAPE, happy birthday, Giorgiana. The goal is to intensify the international efforts and to build and coordinate a robust network of collaborations. And the main answer that we wanted to address in the frame of this expert group is to answer a variety of weather, such as precipitable water vapor and space weather related needs, like for the ionized layer. And to do that, the goal was to make some data sharing and to make some model developments. So I already presented this slide this morning in UTC, where we consider ionospheric as ionized layers as the ionosphere and plasmasphere, neutral atmosphere as thermosphere and troposphere, and also consider the magnetosphere. So within GRAPE, since during the last 10 years, we had several publications, 60 papers, and a special issue in Annals of Geophysics. And we also had the GRAPE white paper, which was published in 2021, I think, 2020, sorry. We made a lot of reports for SCAR, and we also participated in conferences, workshop, training, and capacity building. We participated in all the SCAR open science conferences since 2012. We also participated in URC, in Beacon Satellite Symposium, in URC Gas, and we had one meeting at ROB in 2017. One of the main achievements also for this network building is to reach young people. And one of the main output of this was the International School of Space Science, which took place in Aquila in 2018 with people from Europe, Asia, Africa, South America, etc., etc. One of the main goals of GRAPE was to make some platform for data sharing, and also to standardize historical and real-time observation. So this is made through this INGV web portal, mainly for scintillation receivers. We also have the chain from Canada, the chain program, which stands for you have Renaissance, you have GPS and scintillation receivers. And you also have this CEDAR Madrigal web portal, which is a portal for general upper atmosphere models and data on a worldwide perspective. During the last 2 years, we organized an online workshop from the one to the, it was a 3 days workshop in July 2020. We had 70 online participants and 35 talks, mainly focused on the mesosphere, thermosphere, troposphere, plasmaspheric, ionospheric, but also on the space weather impact on radio measurements at high latitudes. So all these conferences, the programs is available in this web address. It was quite a big success. And at the end of this workshop, so we decided to write a white paper for STAR within the GRAPE. It has been published in 2020, in September. It's quite a popular paper. And in this paper, we highlighted 16 urgent questions to be addressed from our community for the neutral part of the atmosphere, and also for the ionized part of the atmosphere, and also for the geomagnetic fields. I won't go in details in all these questions, but you can find all of them in the paper on the SCAR website. So after this paper, this is something that I already presented in the last slot of this session. There are some redundancy between GRAPE and Agatha. I presented this morning. So the main output of this workshop was that we need to enlarge our community. Before we are within GRAPE, we are mainly GNSS, and now to answer all these questions, to answer this question, we need to enlarge our community to other instruments. People interested in other instruments. So for that, with Lucia Alfonsi, we made a review paper with a lot of other co-authors, we have up to 40 co-authors, to review the instrumentation dedicated to geospace and neutral atmosphere data in polar regions, not only in Antarctica, but also in Arctic regions. We used satellite data also, so it's a huge amount of data. So you can see the left and the right, the ground instrumentation that we have, which is quite growing since the first International Geophysical Year in 1958, for example. This paper is accepted with minor revisions in Surveys in Geophysics. So as I showed this morning, but I just sent these pictures to show you other examples. The goal is to get the long-term properties of the neutral and ionized atmospheric layers. On the left is an example for different months of the integrated precipitable water vapor in Antarctica and Arctic regions, so in January and July. So this is made by models, and actually we compare the outputs from GNSS, for example, with this kind of models here. And on the right is a picture with a median monthly median total electron content behavior over the Antarctic Peninsula, so from January to December, using 20 years of data. So it's a huge amount of data. And what you can see here, for example, is that an interesting result that we had in this paper is that we can see the weather sea anomaly with a maximum total electron content at local midnight time, which is during summertime in Antarctica. The other example
Nicolas,
that
you have two minutes more.
I finished. Thank you. The multi-instrumental studies is mainly dedicated for extreme events such as coronal mass ejection impact, solar flares, etc., etc. And to illustrate one example, we took this 2019 May event. Sorry, you can see here the ground measurement of the geomagnetic observations, the total electron content extracted from GNSS receiver, the ROT, the rate of tech, also, and also the scintillation index sigma phi. And in comparison here, we have totally other methods. So you have geomagnetic, GNSS mainly based, and optical all-sky imager data in a wavelength of 630 nanometers. So we have a good correlation in between the active activities seen in the all-sky imager data and the magnetic and total and GNSS-based ionospheric parameters. So GRAPE is planned to be embedded in the proposed planning group Agatha that I presented this morning. In case that this Agatha project is not recommended by the SCAR delegates, GRAPE will continue its activity until the next SCAR Open Science 2024. Apparently, we have some chance to succeed in Agatha. So wait for Agatha, which will GRAPE during the next 10 years, I hope. And for this, we need the answer from the SCAR delegates at the end of September this year. Thank you for your attention. If you have any question.
Okay, thank you, Nicolas. Any question for Nicolas? If not, we can.
I have to leave
thank you again.
I have a nice session. I have to leave you now. Have a nice day.
Bye-bye, Nicolas.
Okay.
Thank you for the
Nicolas.
presentation. Thank
You're
you.
welcome. Bye-bye.
Okay, so we can move to the next presentation given by Luis Thiago Medeiros Raunete. Sorry for pronouncing wrongly your name. The title of the presentation is Gravity Waves Characterization in the Lower Ionosphere using VLF Observation at the Comande Ferraz Brazilian Antarctic Station. It's your turn.
Can you hear me?
Yes, we can see you. We can see your presentation and we can hear you.
I'm sorry,
10 minutes for you, and 2 minutes for the question.
I just shared the wrong screen. Now, are you seeing the presentation?
We see your presentation.
Okay, thank you. As you said, my name is Luis Thiago. I work with Emilia Correia and Giorgiana at the Mackenzie Presbyterian University. And my work is gravity waves characterization in the lower ionosphere using VLF observations at Comandante Ferraz Brazilian Antarctic Station. Well, sorry. Gravity waves are ondulatory phenomena resulting from the imbalance between the forces of gravity, Coriolis, and the pressure gradient or buoyancy. And you can see some of the sources listed on the left, being the most common one, the orographic event, as shown in the figure below, where a mass of air reaches a mountain, and when it passes through this elevation, the gravity pulls it down and the buoyancy pushes it up. And this imbalance between them creates an oscillation that became the wave. This wave propagates upwards in ascendant form at the atmosphere with an exponential growth of amplitude due to the rarefied properties of the upper atmosphere until it breaks and transfers energy to the medium. This transfer of momentum and energy is believed to be an important agent of the atmospheric dynamics. As you can see, some of the effects that it causes is, as I said, the vertical and horizontal transport of energy. It interferes, therefore, with the atmospheric dynamics, and it affects the ozone layer by participating in the formation of polar stratospheric clouds, and it affects the electron density, and it can affect the telecommunications and GPS. Well, gravity waves are mostly investigated using airglow all-sky imagers that give us images like the one on the left. They are fitted with filters that give their characteristics at about 90 kilometers of height at the same region, the D region, where the VLF signal is reflected in the ionosphere. The passage of these gravity waves through the region results in oscillatory perturbation of the electron density that are detected as amplitude and phase fluctuations of the VLF. Here we will investigate their impact on the base of the ionosphere at D region, utilizing very low frequencies radio measurements performed at the EACF. Well, we used three paths to the analysis: NAA EACF, NPM EACF, and NAA ATI. The original data has a temporal resolution of 10 seconds at the blue line, and with a 150 seconds rolling mean, we get the smoothed orange line. The analysis of the phase gives us the horizontal variation and the amplitude, the vertical oscillation. This technique was validated by case studies that presented good association between the gravity waves periods obtained using the VLF technique and using airglow observations. As can be seen in these results, the first case, we have a mesospheric front that was observed with airglow imagers at 10th of July in 2007, with a period of 8 minutes plus minus 2, propagating northeast. It was detected on the wavelet analysis as shown on the left. Here we have two vertical lines, marking the period interval reported. There was a lot of activity. Sorry. The vertical lines marks the time of observation, and the horizontal lines marks the period that the wave was reported. And so we can see that there was a lot of activity around 7 minutes, matching the wave. And the interesting thing in this case is that on the graph A, we can see in green the morphology of the wave at the raw VLF data. We can see the first front wave and 4 crests described in the observations of airglow. It's interesting that when we run the analysis at the phase, we are able to see the same wave but 20 minutes before, which is typical to this form of wave. Mesospheric fronts have the characteristic transition from a vertical gravity wave to a horizontal gravity wave, or in this analysis, it appears before in the phase and then at the amplitude. Here at a close-up, we can see the lag between the two, above the amplitude and down the phase, and the morphology was roughly the same. As the event was detected at the NAA EACF path, which is a long way, why can we say that the activity we saw was the one close to the EACF? Trying to answer this question, we made the analysis of the trajectory between NAA and ATI received at Atibaia. There was no considerable perturbation, as you can see, of intensity at the same interval that the wave was reported, between 2 to 3 hours. So we can eliminate this part of the path, leaving only the region after ATI to contain the gravity wave, restricting the region that the wave can be detected. Now, to show the technique another form of wave, we have a band event occurred on the August 18th of 2007. With observed period of 13.1 plus minus 0.2 minutes propagating northwest. This one had a greater extension and lasted 4 hours as reported by the airglow. The wavelet analysis show activity at the same 12 minutes mark, lasting from 3 to 7 hours. And with an intensity peak at the same time of the time used for the airglow analysis, all matching the report. For the phase, the VLF doesn't show much activity, indicating an event with characteristic horizontal perturbation. The analysis of the VLF from NPM shows similar activity with predominant period around 14 minutes with a 2 hours lag. Although showing the same characteristics to appear before the NPM, the wave had to be propagating northeast which was the opposite to the direction of the airglow report. However, it can mean that the same source or a strong atmospheric condition was generating multiple waves at the region of Antarctica. Well, for the discussion, we can say that these case studies show the high potentiality of VLF as a tool to observe gravity waves in the base of the ionosphere. We can get characteristics such as period, propagation, direction, and amplitude. The two studied cases show signs of gravity wave interfering on the base of the ionosphere, and the properties obtained are similar to the ones getted with airglow observations. VLF has some advantages over the other methods because it's possible to observe 24 hours a day, showing a more detailed timeline of the events, and it's capable of covering a much larger area. To go forward with this research, it will be analyzed a greater interval of time to characterize the predominant period distribution and to evaluate its behavior due to ionosphere variation caused by the solar cycle. Thank you all. I want to say a special thanks to the SCAR 2022 Organizing Committee, to CNPq Pro Antar, to CAP's PhD degree scholarship, and say if there's any one of you that have questions and don't have time to answer, you can send an email to the one listed below. Thank you all.
Thank you, Luis. Tiago. Any question for Luis, Tiago?
I have a question, a short question, Luis. Do you think that you can use also other VLF data from around the world? Because as far as I know, there is a quite good data bank on VLF.
Yes, we have a giant mesh because of the VLF was used in the war to contact submarines. So we have a lot of receivers and emitters, and all of this data, including the ones gathered years before, we can use to run the analysis and get the information.
So it could be interesting also to try to merge your data with the rest of the network and see if you can obtain some more indication concerning the gravity waves detection.
Yes, we are using this one because we have at the same time observations with airglow, so we can validate the technique. But once it has been done, we can do it for any data.
Thank you.
Okay, any other question? Any other question? If not, we move to the following presentation. We are in time because it was scheduled at 14 UT. So it's time for Wojciech Milok, Space Weather Studies at the Troll Ionospheric Observatory in Groningen Maud Land, Antarctica. It's your turn.
Yes, thank you very much for the introduction. So I'll give a presentation on the space weather studies, what we are doing right now at the Troll Ionospheric Observatory in the Groningen Maud Land in Antarctica. This contribution is together with Daria Kotova, Björn Liebeck, and Espen Tronsen, all from the Department of Physics, University of Oslo, Norway. I hope you can see the screen and the slides, because I know that there are some problems, so please give me the
feedback.
Yes,
we can see you. Yes,
Very
we
good.
can see everything.
Thank you. So the Troll Research Station, where it is located in the Groningen Maud Land in East Antarctica, and here you can see on this map the location of Troll, which is close to the Princess Astrid coast. And it's relatively close to Sanaya Station. Relatively, it is about 200 kilometers to the east from southeast from the Sanaya, and on the other side you have Maitri and Novolazarevskaya stations. We also have the Neumayer 3 station, which is also nearby. In the picture below, you can see how the station looks like right now. It is now being upgraded. There are some developments and the big developments in future, and I will be telling you later on about that. Our observatory is located on one of the hills far from the station, so that we have no light pollution from the station. The station itself is located at the altitude of about 1,800 meters, and then we have the mountains, the Nunatak, that is raising up to about 2,000 meters, and then you can see that this is the latest last stop with the permanent overwintering station before the South Pole. The ionospheric observatory at Troll has been established because of the three reasons. The first, of course, is the knowledge. And here we aim to study the aurora australis and structuring of the turbulence in the ionosphere. You can see in this figure that based on satellite data, we know that there is a strong asymmetry in the plasma structuring in the polar regions. And here is an example of the study done with the swarm satellites for both rate of change of density index and the gradients of the density. But at the same time, we want to understand and contribute to understanding the asymmetry between the two hemispheres, because we know that the two hemispheres are different. The aurora is different. The response of the polar ionosphere to the geomagnetic activity is different at both hemispheres. So the first is knowledge, but then comes the application with the monitoring and the observations, long-term observations. We want to contribute to the development of the global space weather models, because the society is becoming more and more dependent on the for example, satellite communication and irregularities in the ionosphere. They impact the propagation of the radio waves and hence lead to the scintillation and lower the accuracy of the GNSS systems. The other problems are the strong currents in the ionosphere, which may impact the electric grid system. So there is an ongoing worldwide activity towards the development of the global space models, and so we also are thinking of in these terms. Finally, we want to contribute to the international network with the observatory. So the Troll is located in the top of this map. And you can see that some of the stations, not all, are listed, but some of the stations are listed on this map. And you can see that Neumeier, Sana 4, Lyatskaya, and Maitri, they are in a close proximity of Troll. But also Shiova, Belgrano, and Halle, and so on. So here I have encircled the stations which we have good contacts with, and we can get some contribution. We can contribute to the studies, and also vice versa. Their measurements can contribute to the measurements and analysis of the measurements that we have on our station. So what do we have there at the moment? We have the observatory started in 2018 with the deployment of the GISTM, which is the GNSS Ionospheric Scintillation and Tech Monitor. We have the Novatel GPS Station 6 installed. Here is the antenna mounted on the container. And then we have the all-sky imagers. We have the all-sky imager Geosentry, which was installed in January 2019, with spectral filters for monitoring the auroral dynamics. And we have 3 filters, 660, 557.7, and 428.8 nanometers. In addition, we have the all-sky camera, the Sony Alpha 7, which we also mounted next to the all-sky imager, Geosentry imager, which you can see here in the middle picture, where the Geocentry is the big camera that weighs about 20 kilograms, and then we have the smaller one for cloud monitoring and also monitoring of the aurora in true color to have some redundancy in the system as well. So this is all mounted in the heated containers and with the domes, as I mentioned, on the top of the mountain, and now is in operation. And here I'm showing the first of the case studies that we published based on the data from the station, that is in February, the case study for February 2018. And you can see already the synergy effects where we have to put the stations together. We have the magnetometer data from on Neumeier, and then we have magnetometer data from Sana station, which show the disturbances in the magnetic field, which are related to ionospheric currents. And in addition, we are looking at the sigma phi scintillation indices, which show us the relationship between the structuring of the ionosphere. So we can see that the ionosphere is quite well structured during this onset of the auroral substorm, which is happening around 4 or 5 UT. We do not have much activity in S4, which is also quite in the amplitude scintillation index. That's also in agreement with the overall expectations for the polar regions. But what we can also use is the super darn data from Sana station, which is actually looking right over Troll, and we can see that there are strong flowshares right above Troll. And what we can then also associate this elevated scintillation indices, which I should say these are the irregularities in the ionosphere that are propagating quite fast. They are associated with the flowshares at the edge of the convection pattern during the substorm expansion phase. And we can actually confirm this with the satellite studies. Here we are showing the DMSP satellite data, which here you see the image of the aurora taken from the satellites, and both stations at Troll and Sana next to it, located next to it. And then while we are lucky enough that DMSP satellites were passing right over both stations. And here you can see that when they are crossing, then we also, here's the segment considered for 1 minute segment for the trajectory of DMSP. We can see that there is an elevation in the phase scintillation index. And here with the in-situ measurements with the satellite data, we can actually relate it to the crossing into the auroral oval. So that's the edge of the auroral oval that is most structured. Another example is shown here, and this is from 10-11 May of 2019, which actually Nicolas was showing part of these results in the previous presentation. So here we see that we have the large geomagnetic storm in May 2019, and here's the data from the satellites located in a Lagrangian 1 point, and also with the ground-based measurements. So we have the large activity over Antarctica, and these slides were already presented in the previous presentation, coincidentally, but just to mention that we have a variation in the magnetic field that is related to the substorm activity, which is really strong on that day, and we see that there is a high variation in the rate of change of tech and very high structuring in sigma phi. Just note the time. This is 2:30 UT, And at 2:30 UT, we have the largest coverage of the aurora. We have the expansion of the aurora. This is the green line, and over time, and this big expansion is actually associated with the with this drop in the magnetic H component, which is. But you can also see that the aurora, that was the very active day overall. But in the red light, that's actually the place where we want to be. We see that that's a really high activity during this substorm event. And we can associate it or study it together with the super darn data, and again we can, in this case, associate it with the expansion during the onset, and also of the activity and expansion of the auroral level, and also very strong velocities at the edge of the convection cell. So that's just before 15 minutes before. We have a lot of activity close to our stations, but actually not that close, but because the stations are right here. But we see that there's a lot of signal, and then we expect, I mean, there is the expansion of the whole activity over Antarctic. So there's more analysis on that geomagnetic storm in the paper that has been submitted and now is in press by Lucilla Alfonsi et al. And also there it's indicated that we use actually data from different stations in Antarctica to support the case. What's the future? I think the future is bright for the ionospheric observatory at Troll, because right now we are starting a larger project which is related to the Troll observing network. The project is the large infrastructure project that starts this year and will run for 10 years, funded by the Research Council of Norway. And the Troll observing network is led by the Norwegian Polar Institute, and we are one of the main partners in that project. And it's basically it's a large investment into the Troll station where we'll be developing the different observatories, looking at the whole ionosphere, starting from the ionosphere, which is very important for us, but also going through the middle atmosphere with the infrastrand sound research, and going down to the troposphere. There's also sea and ice research, and also the wildlife monitoring. So this is ongoing. We are starting this now, and I'm happy to share this news that through this TUNE project, we plan to deploy an ionosonde, and we'll be able to study ionospheric structuring and the ionosphere dynamics in a very great detail. And also, in addition, we plan to install a local magnetometer at Troll. So I hope that in a few years to come, we'll have a very good coverage and very good instruments park, as we call it, instrumentation for the ionospheric research, and that will enable even stronger collaboration and data exchange within the community. And with this positive news, I would like to thank you, and I'm happy to take any questions.
Okay, thank you. Yes, I was wondering if you are planning to put a magnetometer, a geomagnetic observatory, and you have said yes. That. So
we are planning, but we know that in neighborhood we have Sonya, relative neighborhood, yeah. 200 kilometers.
Yeah, but Antarctica need to have a much more points of observation.
Yes. So in the first round, it will be the relative magnetometer. So that will be a variometer, just to look at the variations. So we'll
sure.
So yeah. So that's
the starting point. That's the starting point. Okay.
Yeah.
Okay, Giorgiana, you raised your hand.
Yes, thank you. Wojciech, for the interesting presentation. I would like to know what about your facilities to access data in real time and or to receive data, and the construction of a possible database in order to use your data, also to feed maybe models related to the space weather, but also to share all this potential offered by the troll station to the communities within Agatha, hopefully, the new planning group for a program planning group. However, concerning GRAPE, but GRAPE will be within Agatha. But however, this is important for all of us that we work on geospace, generally speaking. This is important that we have data also to feed model in real time. No? If we want to give some contribution to the users of space weather products. Thank you.
Yes, I agree completely. And in fact, this is, I can say this is our contribution to Agatha. And then we are very happy because it also was highly supported. This whole the tuna was had a good feedback from SCAR community. So at the moment we have the data shipped after the season, the raw data, and this has been a problem. Of course, the data transfer from Antarctica is a problem, but the good news is that within tuna we have we also have the data system, and this is included in the project that will have the near real-time access to data, and that will be provided to the servers in Norway and then redistributed to stakeholders. So we will get our data in real time, and that's the consortium is working already on that. The good thing about Troll is that it's also a satellite data receiving station. So there are antennas for receiving data from satellites. So we can start negotiating with these operators and get this link, fast link to Troll provided to us. So there will be data available within a short time and in Antarctic terms, so maybe 1 year or 2 years, once we have it established, and it will be provided first to the servers in Norway and then distributed into the databases. And of course, with the open access data policy as it is for Antarctic data. So okay. This is also bright news.
Okay, thank you again. So we move to the next presentation given by Mohan Agrawal. So the title is Recent Development Towards Deciphering the Low Frequency Radio Universe with Albatros, an upcoming high-resolution interferometer observing from Arctic and subantarctic regions. 10 minutes for you and 2 minutes for questions. We cannot hear you. Your microphone is mute.
Hello.
Yes, we can hear you.
Yeah, so I'm just trying to. It's telling me that my screen sharing is paused. I'm trying to.
Yes, but you are not in the presentation mode. You are not in the presentation mode.
Okay, just a minute. So, okay, I've started sharing the screen.
Yes.
Can you now see my screen
Not,
now?
not in the press. It is still. It seems still not in the
Okay.
presentation now.
Before to
Yeah,
share,
right.
put the presentation in the presentation mode and then share. It should be working.
Okay. Okay, I'll try that. Okay, how about now?
Just a minute, so at least. Yes, it seems okay, but it's
Still not appearing.
No,
Zoom for some reason starts. It loads and then somehow it keeps fluctuating. Is that so?
okay.
You
Mohan,
can go on with
go
this.
ahead. You are not in the presentation mode. It means that you have to click slide by slide. Otherwise, you do not go ahead with the slides, okay? So try. We see your presentation, but not in the presentation mode. So
Okay.
that you had to move the slides. Otherwise, we remain fixed
Okay.
the first one.
Okay, because Zoom for some reason it keeps fluctuating. I don't know why. This has never happened. It fluctuates. It won't let me. Let me just try one last time. Come on.
If you have a PDF or a PPT, you can put your PPT in the chat. And we,
yeah, sure.
And Domenico or myself, we can help you.
Sure.
Managing your presentation.
Can I send a PDF on the chat?
Yes, you can upload.
Okay.
Try.
I'm so sorry. This was absolutely unexpected. Okay. Because I've tried this portal. I tried to use this portal yesterday. It worked absolutely fine. So sorry.
It takes time to be uploaded in the chat. Maybe you can try to.
Yeah, I uploaded it. I uploaded it. It's
okay.
It's
now,
okay. I see.
Okay.
Now I try to.
Okay.
To download. Just a moment.
Sure.
It is already in the chat now.
Yes, I see, Emilia. I'm going to take to open. I do not see. Okay, so I try to share my screen in order that you can see.
Okay.
Okay,
there we
so
go.
let me know when I have to go ahead.
Sure. I will do that. And again, thank you very much for this favor. And again, before I begin, I'll apologize once more for the time lost. So yes, thank you very much. And just to introduce myself again, I'm Mohan from McGill University. And today I will be talking about a new low-frequency radio telescope that we call Albatross that is being deployed by the Radio Cosmology Group here at McGill University. And if you can scroll one. Could you scroll the slide?
Giorgiana, go ahead.
Go ahead, yeah.
Okay. It's okay?
Right.
Yes.
Yeah, it's okay. It's perfectly fine, yes. So Albatross, I'll start with a quick overview. Albatross is an acronym for Array of Long Baseline Antennas for taking radio observations from subantarctic and 79th parallel. Now, as the name suggests, this telescope will be based out of two locations. One is in the Arctic at 79 degrees latitude, which is the Axel Heiberg Island, which is shown on the left image on the top. And the second one is at Marion Island, which is roughly 2,000 kilometers off the coast of South Africa. It's a sub-Antarctic locations. And each of these locations will have 10 antennas, which look like something shown in the bottom image. And please go ahead. Now, the main observational goal of this telescope is to make the most modern, highest resolution maps of the low frequency sky, which is between 1 megahertz and 125 megahertz, which is also the operational range of these telescopes. However, our main focus is between 5 megahertz and 30 megahertz for reasons that I will get to very shortly in the upcoming slides. Now, as we know, resolution of any telescope scales roughly as lambda by d, where lambda is the observing wavelength and d is the diameter of your dish. Now at 5 megahertz, just for example, if we wanted arc-minute resolution, that would mean that we would need a telescope that has a diameter of tens of kilometers, which is not really possible to build, which is why albatross is an interferometer. And the principle of interferometry is quite simple. Instead of having one big dish, we can have several small dishes or several small antennas that are distributed in an area that is equivalent to a big dish. So all the 10 antennas of albatross will have a maximum separation of 20 kilometers in order to enable arc-minute resolution. And once we observe the sky from all of these different locations, then we can combine the data from these telescopes to reconstruct an image of the sky. If you can go ahead. Giorgiana, could you please scroll?
I moved in the for science motivation. Do you see?
No, we cannot see.
We cannot see. Okay. We just saw it.
Okay.
Yeah, we can see it now. Yeah, thank you. So the main science motivation behind building a brand new radio telescope is that we would like to take the very first steps towards observing the so-called dark ages of the universe. So just to put some context, we have already seen the CMB, the cosmic microwave background, that is coming to us from 400,000 years after the Big Bang. And now the JWST will will hunt for some of the very first galaxies that formed roughly 300 million years after the Big Bang. But the phase of the universe before the formation of the first stars, that is where we would really like to get to. And the signal that we expect to come from these dark ages, we expect it to lie between 5 and 30 megahertz, which explains why we are focusing on that. Now, if you can scroll. Yeah. However, the current status of observations in this range between 5 and 30 megahertz is not so good. In fact, in the global sky model, which basically tells you what the sky looks like given a frequency, it has very poor sky coverage and very poor resolution, as you can see in the left plot here on the bottom. It has only 2 inputs in this range, both of which don't look so good. And when we go down to the lowest of frequencies, around 5 megahertz, the state of the art dates back all the way to 1966, which is shown here on the right. So this was probably drawn by hand. And if you can scroll. And similarly, none of the ongoing experiments that are operational right now focus on this range. So on the left is the long wavelength array, which has arc-minute resolution, but at slightly higher frequencies. And on the right is LOFAR, which is based in Netherlands, which does go down to these frequencies, but it has poor resolution. So Albatross is the first experiment that's focusing specifically on dark ages. If we can scroll. So the way Albatross achieves this resolution, as I mentioned, is by having its antennas spread very far away from each other. The location of these antennas, in the case of Marion Island, is shown here on the left plot. And when we combine the information from all of these antennas, we get a synthesized beam on the sky, which looks something shown on the right image. And synthesized beam is basically just the smallest area that we can measure on the sky. And to give a sense of scale, the size of the moon is roughly 30 arc minutes. So we are really probing very small area. We have that capability. If we can scroll. And to illustrate how significant of an improvement in resolution this is going to be, I have shown here sky maps that were produced by the Planck satellite. Now these maps are in microwave. These are not in radio domain. But to show what a 20-fold, 10-fold, 20-fold improvement in resolution looks like. So on the left is an image that was made with a 2-degree beam, 2-degree resolution. And on the right is an image that was made using 7 arc-minute resolution, which is roughly what Albatross will have. So as you can see, all the fine scale structure, small scale structure, all the details, they have all disappeared on the left one, but the right one is very much, it's like we bought a new pair of glasses. Now, if you can scroll. Now, of course, one thing that the natural question that comes to mind when we talk about observations around 10 megahertz is whether or not the ionosphere will let us observe, because as many people here will know, ionosphere becomes opaque below the plasma cutoff frequency because electromagnetic waves cannot propagate below that. But some simulations using international reference ionosphere have shown that at Marian Island, this cutoff frequency might drop as low as 1.5 megahertz during a solar minimum. And which is why we are optimistic that we will go down to at least 5 megahertz. Now, if you can scroll. Another problem, another challenge that we will face and that any radio telescope has to face is that of radio frequency interference, or RFI, which is basically contamination of our data because of all the man-made terrestrial radio signals. In the frequency range where we will operate, which is tens of megahertz, the dominant form of RFI is going to be from shortwave radio transmissions, which bounce off from the ionosphere. But preliminary observations from Marian Island, which are shown here in the image, they have shown that it's actually a very quiet location for radio observations. So the signal that we are looking at here, this fringe pattern, repeatable structure, is from the motion of the galaxy overhead. And below 10 megahertz, the noise really starts to dominate. But the good news is that this is just raw data, and we have done no processing on it. So we hope that with some effort, we will be able to push down below 10 megahertz. And if we can scroll. And finally, I'll just give a very quick overview of the correlation pipeline, which basically its main function is to combine the data from different antennas. Because as I mentioned, to do astronomy with an interferometer, we really need to combine data from pairs of antennas. So we start with raw time streams, literally voltage time streams recorded by each antenna. We extract the relevant frequencies, decompress the data. And then the third step here, the main step, is to apply timing correction to it, because each of these antennas have independent flocks. And whenever we have independent flocks, there will always be some drift between them. So it is possible that the two time streams that we have, they might have some unknown time offset between them. And we want to get rid of this, because if we don't, then this is going to shift the structure of shift all the structures in the sky image that we reconstruct. So we may think Cygnus A is somewhere, but it's actually somewhere else. So this is an ongoing area of research, and we are currently trying to use OrbCom satellites for this. And once this is done, we correlate the data, which is just multiplication in Fourier space, and then store the output. And if you can scroll. So that's really it. Just to summarize, Albatross is a new radio telescope that's taking the very first steps towards observing dark ages. It will observe the low frequency sky at unprecedented resolution. It's based at Arctic and subantarctic locations. And one of the active areas of research right now is to synchronize time streams between different antennas. And thank you very much.
Thank you.
Yeah, two minutes over, but thank you very much for bearing with me.
Okay, thank you, Mohan. Okay,
yeah.
Thank you. Any question for Mohan Agrawal? Okay.
No, Domenico,
Giorgiana.
it is very, very interesting. I am not an expert, but I understand that with this kind of radio interferometer, you could give better and detailed information in respect to LOFAR. Am I right?
Right. With respect to LOFAR, yes, we are trying to improve on LOFAR when it comes to lower frequencies. So LOFAR recently introduced an upgrade that goes down to 10 megahertz, but the resolution that they have is a degree resolution, because LOFAR was not built specifically for 10 megahertz. LOFAR was built for 30 megahertz and above. Okay. So we are trying to build this instrument specifically targeting the low frequency sky. Yeah.
Okay, so you were saying that you can also see, or in some way you could also investigate the lower part of the ionosphere.
Right.
Because if you are around 2 megahertz,
right,
of course you can give some inputs also to ionospheric physics.
Right, exactly. So another idea behind Albatross was that we will bracket the cutoff frequency. So if the cutoff frequency, let's say, is 5 megahertz, then we will image at 2 megahertz, and then we will also image at 10 megahertz, so that we have something to say about, at least we hope we'll have something to say about different layers of the ionosphere.
Okay,
yeah,
I am curious, but it's too long to know what about the operational questions related to this kind of instrument,
right,
interferometer, because you have several antenna,
different locations,
antenna, and you have to maintain, to manage also the data.
Yeah.
So it will be not simple, but however, you are in the first stage, in the first phase of this
yes.
project. So
yes,
thank you.
In fact, thank you.
Thank you.
Okay, so yeah, you were 5 minutes late, so it's time to leave the space for Pamela Janinska, Albatross from front-end electronics development for low-frequency radio observations from the sub-Antarctic and Arctic. You belong to the same team, I suppose. So.
Yeah, exactly. We're from the same group. So I hope the talk is complementary.
Okay,
so also you want that I help you, or you can try to do by yourself?
Let's check. We can see your presentation. Yes.
Okay, let me go into presentation mode.
Yeah.
Can you see the slides properly?
Perfectly.
Excellent.
Perfect. Okay, I'm happy. Okay, so can you hear me properly? Everything is okay?
Everything is okay. You can
Perfect.
go on.
Thank you so much. Thank you so much. All right. So hello, everyone. My name is Pamela Janinska. I am a master's student at McGill, working with Professor Cynthia Cheng in cosmology instrumentation. So today I will talk about the Albatross instrumentation, focusing on low frequency front-end development. Our universe is filled with lots of neutral hydrogen, which naturally emits light at a wavelength of 21 centimeters. So in radio astronomy, this is precisely what we want to do. We want to measure this emission, and the signal we're looking at is this natural flow from hydrogen. As the universe is expanding, the light emitted by an astrophysical object would be redshifted or stretched as it travels towards us. So if you look at light that has been stretched to a particular frequency, to a particular wavelength, and you tune your telescope to that wavelength or observational frequency, then you can measure a specific part of the universe's history. So now we go to very low frequencies, meaning really early times in the universe. And the epoch that we're going to focus on is this period called the Cosmic Dark Ages. As my colleague mentioned, this is very interesting epoch because no cosmology measurements exist yet to probe the evolution of the universe at those early times. Of course, there is a catch. It's very, very difficult. And in fact, this is the current state-of-the-art map at low frequencies taken in the 60s, which is the lowest that we have measured so far. There are a few other low frequency experiments with very poor resolution, as you can see on the table, but the bottom line is we need more observational data below 30 megahertz to understand what the radio sky looks like. So this is our goal. We want to create better, high resolution maps at these low frequencies in comparison to the existing map from 60 years ago. And this is what we want to do with our experiment called Albatross. We want to map the radio sky below 30 megahertz by building an interferometer array, or essentially installing multiple antennas. By having a baseline of 10-20 kilometers for our instrument, we can obtain an order of magnitude improvement in resolution compared to other low frequency sky maps. Choosing the correct deployment site for our interferometer is an essential step for successful sky measurement. The sites of Albatross arrays are selected such that they can have an overall low negligible RFI. And as my colleague mentioned earlier, we have antennas installed at Marion Island and at Mars, the McGill Arctic Research Station. But there is also a third deployment site, which is called Opishka Research Station in the northern Quebec, which is not as radio quiet, but it is extremely easily accessible and serves as a perfect test bed for our Albatross subsystems. So things like extreme climate and limited access to Mars and Marion Island require a physically robust and autonomously operating instrument which can collect and store data for offline correlation. Each antenna station is equipped with a dual polarization dipole antenna, active front-end electronics, back-end electronics, a large data storage system, and we have a power supply system. The completed Albatross array would consist of 10 autonomous antenna stations, and now I'm going to show you in order of the signal flow what each piece looks like in more detail. Starting with Albatross antenna and front end. So Albatross employs a LWA dual polarization dipole antenna. But unfortunately, the operational range of the LWA is in the order of 20 to 80 megahertz. And there is a significant drop-off in the antenna's response at lower frequencies. Therefore, we need new antenna and front-end electronics, which are optimized for frequencies below 30 megahertz. One thing to note is that the signal we are aiming to detect is very weak compared to the human-made RFI and ionospheric interference. Therefore, we need to make sure to inject as little noise as possible to our system. To ensure peak amplification at the right frequencies, it's necessary that we select the correct components for our front-end board. So our amplifier circuit is based on an instrumentational amplifier, which consists of 3 op-amps or operational amplifiers. The first 2 op-amps are coupled to create the first stage, and the third one amplifies the differential mode of the first stage output. So the take-home message here is we have built an amplifier, and as the name suggests, it amplifies or it boosts the sky signal using electronic components, which we have very carefully selected. So what are some of the tests that we do in the lab with our front-end board? First, we focus on measuring how the gain of the board varies as a function of time, frequency. This is the so-called transfer function. We want it to be as smooth as possible in the 1 to 30 megahertz frequency range. Another important characteristic that we look at is the noise due to thermal fluctuations in the circuit components or the noise spectrum. It has to be as low as possible to maximize the SNR of our measurements. And of course, an essential step in building new front-end electronics is to actually test the system in the field. So we have tested our new front end and compared its performance against the LWA front end. So here you can see the power spectra obtained by observing the sky at Opishka station. You can see that the LWA front end has a significant drop off below 30 megahertz, but in contrast, our front end is very flat at these low frequencies. There is, of course, some RFI contamination as the site is not as remote, but overall, we can notice a significant improvement in the frequency response of our front end. Okay, so now we move on to the next subsystem for Albatross, and this is the back-end electronics. At the back end, received radio frequency signals are processed and digitized. Those are housed in a Faraday cage, which prevents the antenna from picking up any self-generated RFI. So this aluminum enclosure that you see on the photo is divided into two sections. At the top side, when signals arrive at back-end electronics, they're processed by one of the two identical analog signal chains. On the other side of the wall, we have the snap board, which digitizes the outputs of the two RFI signals. At the bottom side, or to the right in the picture, we have the GPS reference clock, we have a Raspberry Pi, and we have voltage regulators. The Pi controls the snap, and it receives the data products. So what makes back-end electronics so unique for Albatross is that they are very portable and also very low, they have very low power consumption. The Albatross autonomous antenna stations must be left unattended for very long periods of time. Therefore, we have large amounts of data which are collected and must be stored for later retrieval. We have two types of data which are produced by the snap board. We have baseband and directly computed spectra. As you can see on the table, directly correlated spectra can easily be stored on SD card, but in contrast, baseband data requires a bank hard drives, which would be connected to the Raspberry Pi via a custom-built USB multiplexer. So at Mars, the best observing period is during the winter. In contrast to Marian Island, at Mars, we can't use solar panels due to polar night. So to tackle this problem, we're going to use a hybrid solar methanol power system, which was specifically designed for extreme climates like the Arctic by a company named SFC Energy. So this system uses a methanol fuel cell, two solar panels, and a battery. The solar panels provide the necessary power during the summer, while the methanol fuel cell takes over the power generation in the winter. So the fuel cell, together with the batteries and our back-end electronics and MUX enclosures, are kept inside a large thermally controlled case. You can see on the photo. So to summarize, the Albatross experiment will pave the way for mapping the low frequency radio sky. This is made possible by building antenna stations, which can operate autonomously in extreme Arctic conditions. Also by improving the performance of our subsystems. And of course, deploying the experiment to the chosen radio quiet locations. So this is where my talk ends. I would be happy to take any questions, and I would like to thank the organizers for.
Thank you, Pamela. Thank you, Pamela. Any question for Pamela?
I have just a comment to Pamela, but also to Mohan. I am not sure that what you say about the best location to install, to deploy your albatros is the polar or subarollar region, because the ionosphere, it seems to you, not so variable, let's say. This is not. So you have to be careful and to test your data. But however, we can help in trying to with the grape group or the agada group could be, of course, interested in helping to remove the ionospheric effect on your data.
Yeah, absolutely. We do expect that. Yeah, we absolutely expect that ionosphere will be a problem that we will have to handle. We will have to compensate for all the delays, and we definitely expect to interact with more of the ionospheric observatories that are there operating from the poles. We definitely, thank you.
You are welcome. So, Domenico, I think we can move to the last presentation.
Yes.
But
So,
excuse me, I think there is a question somebody has posted on chat. Yeah.
Please.
The question is, how do you distinguish? Yeah, yes.
Pamela, how do you distinguish between cosmic radio sources and man-made radio interference? A question for you. Pamela? Pamela left the... Pamela, are you here?
No, I suppose she had some problem because at a certain point she was
disappeared. Okay.
Yes, she was frozen. So maybe the question will be postponed, or you can, or the person can contact directly Pamela Janiska. So the last presentation will be given by Emilia Correia, Domenico.
Okay. And the title is Characterization of the Ionosphere Response in the South American Sector to the 30 March 2022 Solar Event. So please.
Hi, everybody. You are seeing my screen?
Yes.
Yes, okay.
We can hear you.
Well, I will present. Don't move. Let's see. No, it's going now. Okay. Well, I will present the impact of this big solar event of the actual solar cycle in the ionosphere in the American sector. This is my outline of presentation, okay? Like Shipra said, she presented a good effect of solar flares. Then here I will just present the impact in the ionosphere. I will not explain how is a solar explosion. Well, the increase of solar emission affects the conditions of ionosphere, and this affects the radio propagation, and could produce blackouts in radio communication and between other effects, and also in the navigation in systems using GPS. Here we present the effect of this event because it caused the blackout of about 30 minutes in the American sector. And the idea is to understand how was the behavior of the ionosphere during this strong event. Here is the forecast predicted for this strong event. It was a X1.3. It occurs on 3rd March at 17:37 UTC, more or less. Here is the event, and it was forecast a wide area of HF blackouts and problems in low frequency communication for about 1 hour, okay? Here is the dynamic spectrum during the event. that here we can see the blackout producing shortwave communication from about 70-30 UT for about 30 minutes. This bright emission is the solar emission at 30 megahertz, okay? Then there is a blackout in the communication as expected, but it only lived for about 30 minutes, not 1 hour as expected. Here to study the ionospheric behavior, we use many instruments, since from magnetometers to have an idea about the ionospheric currents, GPS, ionosonde, and 2 rheometers, one at low latitudes and in the Caribbean region and at the Brazilian Antarctic station. These are the stations used in this work and the deep latitude of each one. Here is the impact in the magnetic surface, magnetic field surface. To see the impact, we use the 3 stations, 2 near at low latitudes and 1 at middle latitudes. We can see that during the strong event, the magnetic field suffered a fast variation that was in the same direction of the solar quiet daily variation. What means it was positive at low latitudes, following the normal SQ variation, and negative at middle latitudes. And the variation takes about 1 hour, starting just not just in the beginning of the solar event, but 10 minutes after the beginning, during the solar flux was at higher level. Here is the answer of the ionosphere obtained from ionosonde observations done at different stations, at near equatorial extension, São Luís, Fortaleza, e at middle latitudes in Campo Grande, Cachoeira Paulista in American sector. We can see that at F layer from 2000 above of height, we have no much impact in the the critical frequency of the ionosphere, and also in the height of the maximum density. There is no much disturbances at that place, but the minimum frequency of F layer shows an increase of about 3 megahertz during the main phase of the solar event, reaching increased 3 megahertz just coinciding with the peak of the solar event. There are not much disturbance at high altitudes, but if you look at the A layer at around say 100 kilometers, we have a strong disturbance with the E layer disappearing during the highest flux of the solar event. The blackout in the E layer started first at the frequencies nearby at low latitudes, nearby the equator, and it is just have the blackout in the mid-latitude stations when the magnetic field suffered the sudden variation due to the solar event, okay? It only recovered after the maximum of the solar event, after 18 UT, starting recovering first in the stations at low latitude and in just recovering mid latitudes almost 30 minutes afterwards. From GPS measurements, we can see that here is the delta VTC measured from latitudes, low latitude stations at low latitudes to high latitudes in the Antarctica. We can see that the TC variation presents a sudden disturbance just in coincidence with the magnetic disturbance. This black dashed line here is the start of the interference in the magnetic field. And the variation in TC was not so big and just stopped at about 30 minutes after the beginning of disturbance. Then the influence in the total electron content, it was only present in the first 30 minutes. Here is the measurements using rheometers about the cosmic noise absorption. Here, the black line is the station at the Caribbean region in Arecibo, and the blue one is in Brazilian Antarctic Station. Then we can see that they have a similar cosmic noise absorption, being stronger at low latitude, stronger and long-lived. And at the Brazilian Antarctic Station, both started at 17:30 minutes, coinciding with the sunny variation in magnetic field. And at the high latitude, it takes only 30 minutes of duration, while at the low latitude, it was stronger and extended long. But both occurred in association with magnetic field variations. Well, in summary, I'm just quick. Well, the ionospheric response to this big solar event was investigated, and the main results are the sudden enhancements in the global ionospheric currents was produced by this event, or what means the variations in magnetic field was just produced by the photoionization improvement due to the X-ray emission of solar radiation. F layers show no significant variations in density level at about 300 kilometers. Only the minimum frequency increased about 3 megahertz, while on the other hand, the layer practically was strongly disturbed with a blanking of about 40 minutes, okay? Disappearing first at low latitudes and followed by at middle latitudes. TC measurements also shows an increase that started just in coincidence with the magnetic field variation, and it returned in 30 minutes, returned to the preferred levels in 30 minutes. Conclusions of the disturbance occurred mainly from 1713 to 18. The time period, the global ionospheric currents were intensified due to the increase of solar photoionization produced by the X-ray emission of the event. The ionospheric effects were mostly prominent at the lower ionospheric layers, or what means in E and D layers, as showed by the ionosonde rheometer VLF not shown here, but the impact was most in the lower level of ionosphere. And these terms occur in short association with the blackouts observed in shortwave that extend 30 minutes. The blackout occurred just during the F minimum, increased about 3 megahertz. The E layer disappeared, and there is a significant CNA, cosmic noise absorption event. Okay, this is the main results. Thank you, everybody. I just invite you to submit a paper to a special issue of Atmospheric Junior related to recent advances in ionosphere observation investigation. This is the link if you want. Okay, thank you very much.
Okay, okay. Thank you, Emilia. Thank you. Any question for Emilia?
I have a question.
Yes, please.
So why would E layer vanish when there is a disturbance? Like
Shreedevi,
what?
We lost.
Can you hear me?
No.
Yes, now
yes.
completely.
Yes.
Okay, sorry. Yeah. So so I was asking that your results show that the E region vanished during the 30 minutes of the disturbance, right?
Yes.
Yeah. Why would E region vanish?
Why?
Why E region disappears during that period? Because you
okay.
have mentioned that the ionospheric currents enhance.
Yes.
So if
Mhm.
the ionospheric currents enhance means okay, probably if it is equatorial region, there would be a strong uplift of the ionosphere, and then the recombination would become lesser, right? So I was guessing that the opposite would happen, but since you said that it vanishes, I'm just curious to know that what is the process that could have caused it.
No, that's because the X-ray emission, the photoionization of this radiation is mostly at low latitude, around, well, during the day, around 17 or 60 height of in atmosphere. Then the increase of the steel was very high at this low level. Then the frequencies of ionosphere in the region didn't reach there because were absorbed in this
Okay,
low
got
level.
it. Yeah. Okay,
Okay.
got it. Yeah. Okay.
Uh-huh.
Yes. So you're talking about the blackout of the frequencies. I imagine, I assumed that it would be the electron densities as such. That's
No,
why I
no,
just
it was in
calculated it.
frequency. Well, the waves with this range of
Mhm.
frequencies didn't reach
Yeah.
this height. Is this one?
Yes, because
Okay.
a D region enhances and there is a lot of activity going on there, right? Got it. Yeah. Thank you.
Yes.
Yeah.
Okay, so this was the last presentation. I would like to thank all the participants and to invite you to visit the e-poster session. So please have a look of the poster session, and in case of some interest, please contact the authors directly, writing by email, because this is maybe the best way to contact the authors. Giorgiana, do you want to close this session?
I want to, of course, to thank all the people here today. We were mostly the time around 30 people between panelists and attendees. We would like also to thank the SCAR LOC ICT team for their support to have this online big conference, and I hope to see you again soon. At least please have a look to the chat, at least the next year in Japan for the International Union of Radio Science General Assembly and Scientific Symposium, where we will have a dedicated session on the polar atmosphere, ionosphere, and geospace in general. Today, we also had the opportunity to listen something more from the interferometer studies and groups. That is interesting. We hope you will be you will be in touch with us, Grape and or Agatha. Agatha now, as you know, is should be a new program planning group that should be endorsed by SCAR in September, when we will have the delegates meeting. But however, the physical science group support Agatha, and so Grape will finish to go to be included within Agatha. As always, really it was fantastic to talk with you, at least to meet you, at least in a virtual way, and I hope to see you very soon and to be in contact, because the first things for us, for polar science in general, generally speaking, is to be in contact, to share our knowledge, to share our data, to share our model, and to of course, and to be active in trying to train the young scientists, the students and young scientists. This is very, very important. So thank you very much. Please, if you can, I would like to take a picture. Let me see if it is possible. I don't know, but however, I will try.
Turn
So
on your
please,
video. Okay.
I would like to see every people now. Okay. Cheers. Thank you very much.
Thank you, all of you.
See you.
Thank
A
you.
big
Bye-bye.
embrace.
Bye.
All.
Bye-bye.
Bye-bye.
Yeah.
Bye-bye.
Bye-bye.
Bye, everybody. Nice to see you.
Thank
you so much.
Hmm?